So the answer to this is doesn't change. Okay. Likewise, at the freezing point, if you take ice water, for example, and you put it into the refrigerator at the freezing point of water, and you come back tomorrow, it will still have the same amount of ice and water, because at that temperature they coexist happily together. Now, if you put it in the freezer below the freezing point of water, which all of our freezers are set up to do, then gradually it will get cold enough that not all of the kinetic energy, but enough kinetic energy has been removed from the system that it solidifies. Okay? During that process of going from solid coexisting with a liquid, before it all solidifies, the temperature stays at 0 degrees C in that bottle. So even though the outside environment might be, -4 degrees C, inside that bottle the temperature stays at 0 while you have both solid and liquid. It's bizarre. Okay, energy is either released is here, or absorbed or released during a phase change. Okay, so what's happening to that energy right here? The same amount of energy is going into the system, right? You didn't change the temperature of the fire or something like that. That energy is going into changing the phase rather than making the temperature go up. Does that make sense? Here are the answers on that slide, if anybody needs them. Here are some terms associated with the energy of phase change. And we're going to go through and define these one by one. But somebody give me an idea of what you think what does endo sound like?
In.
In. Good. Going in. So therm. Okay, what do we use to measure temperature?
A thermos.
A thermometer, right? So endotherm sounds like there's heat going in, right? Yes. Okay, so heat going in, is that an absorption or a release of energy? Grant?
Absorption.
It's an absorption of energy. Now, what's counterintuitive to this is when you are touching something that is going through an endothermic transition, it feels cold. Even though it is getting more energy in it, it feels cold. The reason for that is that it is pulling heat out of your hand. It absorbs energy. So if you hold a piece of ice in your hand, that ice is absorbing energy out of your hand and moving from a solid state to a liquid state. So moving from solid to liquid is an endothermic reaction, but ice feels cold. That's why ice feels cold, is that it is pulling energy, thermal energy, out of your hand. So think of another situation in which your skin might feel cooler based on being in contact with water. Sweat is what I was going for. When you sweat, the reason your body sweats is that it perceives your core temperature as being too hot. And so you sweat or perspire or glisten, depending. And that water that's on the surface of your body starts to evaporate. Evaporation requires energy, right? We're putting in energy to make this water become a vapor. It's endothermic. So what it does as it's evaporating is actually it pulls heat out of your body to make it turn into a vapor. So that's why sweating cools you down. It's because that is an endothermic.
Sweating cools us down.
That's what sweating is for.
And then
Exothermic is the opposite. So what does exothermic look like?
a description of a non-change in which the system does not absorb. It lets out energy.
It releases energy. Good. A description of a change in which the system releases energy. So if you put your hand into an exothermic situation, it's going to feel hot. Good. If you take little tiny iron filings, little tiny shreds of iron, and you put it in a little package, and you shake that package, the iron filings start rusting very rapidly. This is an exothermic reaction, and it makes the little package feel warm. That's how most hand warmers work.